Good morning, everyone. Thanks for the invitation to the conference. It looks like a fantastic workshop, and I'm looking forward to all of the talks over the next few days. So this work that I'll talk about today is joint work with a fantastic PhD student in our Department of Statistics and Data Science, Ren Yuan, or he goes by Jack Ma. Unfortunately for me, this is not the founder of Alibaba China. That is a different Jack Ma. So I'll do this talk in a sort of reverse order. I want to open the talk with just a couple of open questions that motivated this work. The first question is loosely motivated by a problem of graph matching, which you can think about as the following. Suppose I give you two, let's say, social networks on the same individuals, let's say a LinkedIn network and a Twitter network. And the first network has, Alice, Bob, Charlie, the people, and you see the names of the people in the first network. And the second network is anonymized, right? So you don't know who the individuals are in the second network. The graph matching question is, using just the topology of the two graphs, can you try to identify what is the latent matching or permutation of the individuals that maps one graph to the other? Okay. And one very intuitive and common formulation of this problem would be the following. That if I give you two matrices that represent the graphs, for example, the adjacency matrices, but you can also do fancier things, then you want to find a permutation that when you apply it to both the rows and columns of A, it best matches B. So it minimizes the Frobenius norm squared, let's say. And to make this objective quadratic looking, I can cycle one of the permutations to the other side. This is exactly the same thing. Yeah. So this problem as an optimization over permutations is computationally intractable. And so one method that's popular in practice that people use is this convex relaxation that was introduced by Zaslavsky, Bach, and Verret in 2008, which is to minimize the same quadratic objective subject to a relaxed constraint that the matrix X belongs to the convex hull of the permutation. So this is the Birkhoff polytope. And the first open question I want to ask is this. Let's consider a null setting where maybe there's actually no correlation between the graphs. So A and B are independent GOE or Erdős-Rényi matrices. Asymptotically, as n goes to infinity, what should be the behavior of this optimization problem? So the simplest question one can ask is, what is the limit of the minimum objective value? But of course, for the graph matching application, maybe the question you're actually interested in is if there's some correlation between the two matrices, what is the structure of the minimizer, right? But even in the null setting, I think this question is wide open right now. So this is the question that's motivated our work. To connect this a little bit to the subject of my talk, I think it's informative to take this quadratic objective and rewrite it in terms of the vectorization of X. So instead of an m by m matrix, I just vectorize X into an n squared length vector, in which case the quadratic form is defined by this Kronecker-product type matrix, A Kroneckered with an m by n identity minus the m by n identity Kroneckered with B, and this is in an n squared by n squared matrix. So a second question, if you don't care about graph matching or convex relaxations, I learned a variant of this problem from Justin Ko last summer. It's the following. Consider a lattice, a square lattice, and on this lattice, I put +1, -1 variables. So it's a spin system on this lattice. And we define the Hamiltonian that looks like this. It's the trace of A times X transpose X plus the trace of BX X transpose. And in words, what this represents is the entries of A's control the couplings between row inner products of X, and the entries of B control the couplings between column, I think I got that backwards. So A controls the inner couplings between column inner products of X, and B controls the couplings between row inner products of X. And I can define from this Hamiltonian a Gibbs measure over this lattice. So I define a probability measure in the usual way, where the distribution is proportional to the exponential of beta times this Hamiltonian. And again, this Hamiltonian takes this Kronecker-product kind of form. If I write it in terms of the vectorized version of X as a vector of length n squared, the Hamiltonian has this quadratic term that's defined by an A Kronecker I plus I Kronecker B. Okay. And one can ask the usual or natural question for this model, which is, okay, suppose that A and B are GOE and they're independent. As n goes to infinity, what is the limit of the free energy? And this is a preliminary question to asking more detailed questions about, what is the structure of the Gibbs measure? Yeah. So I find these questions quite fascinating. Partly because it represents a sort of structured regime of mean field theory. In the last 10 or so years in statistical inference and high-dimensional statistics, these kinds of asymptotic mean field analyses have yielded important insight into a lot of problems. I think this audience might be most familiar with the first class of these problems, which are problems of linear or ridge regression. Recently, they've attracted a lot of interest in terms of random features models or in kernelized domains because of connections to neural networks. In this first class of problems, you can typically analyze using asymptotic random matrix theory tools. There's also been developments around nonlinear regression problems like lasso regression or robust regression, around logistic regression and classification, around variational inference. These latter problems, because they're a little bit less linear, they tend to use techniques that are a little bit more than just pure random matrix theory. They involve things like approximate message passing algorithms or Gaussian comparison inequalities or cavity method kinds of ideas. But on some level, they're also related to the techniques that we use in random matrix theory. And the two questions that I mentioned on the preceding slides, they seem to have a different flavor than this large body of work that's been done, in the sense that the variable that we're interested in is not just a high-dimensional vector, but it's a high-dimensional matrix, n by n. The row and column structure of the matrix play an important role in those problems. And also importantly, the total amount of randomness that we're assuming in the problem definition, like the randomness in those matrices A and B, the dimension of that randomness is comparable to the dimension of the optimization variable x. Right? So those problems seem to belong to a different regime of problems than what's been studied here. I realize this is a conference about neural network training, and I do want to apologize to this audience that this talk is not very much about neural networks. But maybe a very loose analogy is that I think the current status of our understanding of mean field dynamics for neural networks maybe is also more developed for settings where we're learning something that looks more like a vector-valued parameter than something that's a full matrix-valued parameter. So the high-level open question that's motivating a lot of what I'm going to talk about is perhaps this one, which is how does one perform asymptotic analyses for this class of matrix-valued problems with this Kronecker structure? So in this talk, I'm not going to give an answer to this question. It's pretty open. But what we did in this work is to try to write down a very simple version of a problem that belongs to this class that we could figure out how to analyze. And this simple version of the problem is going to belong to this first class of problems. I'm going to write down a purely quadratic and linear problem that we can then analyze using random matrix theory techniques. And hopefully, by going through this analysis, we can gain some insight or intuition for how the theory might go for some of these more nonlinear examples. Okay. So what I'm actually going to talk about in this talk is this particular problem here. It's a constrained least squares problem. I want to minimize an objective function. That's this xa plus bx kind of thing that you saw earlier, squared sum in this case. I'm going to add to this a ridge penalty. And subject it to a linear constraint so that the solution is not trivially at 0. Okay? And in the context of this problem, I want to describe to you a theorem which I can state informally as follows. So if A and B defining this problem are independent Wigner matrices, and these ridge parameters and the linear constraint parameters are deterministic, then asymptotically as n goes to infinity, if the empirical laws of coordinates of these defining parameters converge to some limit, then there exists a deterministic limit value for this objective. And furthermore, if I want to understand the structure of this minimizer, if I hit it by deterministic test vectors u prime and v prime, there also exists a deterministic limit value for this. And I'll describe to you what is the form of this value later in the talk. I just want to state informally here. This special case, if you're wondering why we're not just restricting to a pure ridge penalty with ridge penalty 1, we studied that special case in a work a couple years ago motivated by this graph matching problem. I just want to say that that case is actually quite special for a reason that the underlying matrices in the problems commute. And once you lose that commutativity, the problem becomes very different. And so I'm not going to talk about that case today. So because this problem is purely quadratic, it's a quadratic optimization subject to a linear constraint, you can write down explicitly the solution to the problem. And you'll see that the analysis of this question is very closely related to trying to understand the resolvent of a particular random matrix. And the random matrix looks something like this. I'm going to refer to this as a Kronecker deformed Wigner model. It's a Kronecker product of a Wigner matrix A with this m by n identity, plus the identity Kroneckered with B, this independent Wigner matrix, plus a Kronecker of two diagonal matrices, theta and xi. And these would correspond to the ridge penalties I had on the previous slide. So we felt that this model actually was interesting enough on its own right to study from a purely random matrix theory perspective. And so we also carried out just a random matrix analysis of this problem. And our main result here, I'll state informally here, and I'll give you more quantitative and more fleshed out statements later, is that there is a diagonal deterministic equivalent for the resolvent of this model. One sense in which this is an equivalent is that if I take deterministic test vectors and I hit the resolvent by these test vectors, I look at this quadratic form, it's approximated by the quadratic form defined by this deterministic diagonal matrix. And one thing that's cute or peculiar about this class of models that I think might also be relevant for these nonlinear problems I mentioned earlier is that this problem has a two-tiered mean field structure because of this row and column structure. And it's reflected in the structure of the resolvent here in this way, that the pure diagonal entries of the resolvent are order 1. The partial off-diagonal entries, meaning I take a diagonal element in the first Kronecker factor, but off-diagonal the second, those are on a smaller scale, order 1 over root n, and then the fully off-diagonal entries are on a scale of 1 over n. And I think it's probably easiest to just illustrate this in a picture. So this is just a numerical simulation for n equals 20. So it's a 400 by 400 resolvent matrix. And I'm showing you the modulus of the entries of the resolvent. So on the diagonal, you see these large order 1 entries. And you see these sort of faint 20 by 20 blocks. These are the partial off-diagonal entries. You also see these stripes off the diagonal. These are the partial, they're the off-diagonal entries in the other Kronecker factor. And then the fully off-diagonal entries are 1 over n. Okay, so this is a picture of what I'm explaining. Okay, so the outline for the rest of the talk, what I want to do is hopefully the following 3 things. So I just want to very quickly go through some background on the actual deformed Wigner model, the classical one in random matrix theory, just so everyone's on the same page. And this will allow me to state more formally what are our main results in this work. And hopefully at the end I'll have a little bit of time to explain some of the ideas of the proof, and in particular some aspects of the analyses that are different from scalar valued random matrix models. Okay. Great, so I just have 3 slides of background on this deformed Wigner model. I want to explain three things. So the deformed Wigner model is the following. I have a Wigner matrix A, and I add to this a diagonal deterministic matrix theta. Okay, so it's this sum of these 2 things. And the first thing I want to review is that, so if asymptotically the distribution of diagonal entries of theta converges weakly to some limit measure nu, then the spectral distribution of this matrix Q converges also to a limit. This was shown by Pasteur in 1972. This limit is a special case of what's now called the free additive convolution of the semicircle law with this limit nu that was developed by Voiculescu in 91. And in this case, where A is just Wigner and the first distribution is a semicircle, the Stieltjes transform of this limit measure is characterized by a fixed point equation. Okay, it's that the Stieltjes transform is the integral against the limit measure nu of the law of theta of this quantity 1 over theta minus z minus m. Okay, so this is the fixed point equation. The second thing I want to review is that so this is a qualitative statement. It's just saying weak convergence. If I want to make the statement a bit more quantitative, and if I also want to produce an approximation for the resolvent, it's more helpful to think about the free convolution directly with the empirical distribution of coordinates of theta. So rather than passing to this limit measure nu, let me just take the free convolution of the semicircle with the empirical distribution of n points theta. The Stieltjes transform of that distribution will be defined by the exact same fixed point equation, except that instead of this integral against nu, I just have this empirical average over coordinates of theta. And if I take the individual terms of this empirical average and I put them on the diagonal of a matrix that I'm going to call G naught, this defines the deterministic equivalent approximation for the resolvent. Okay? So throughout this talk, what I'm going to mean by deterministic equivalent for the Stieltjes transform will be an object like this, and for the resolvent will be an object like this. And this deformed Wigner model is by now extremely well understood in the random matrix theory literature. So if I denote the actual Stieltjes transform and resolvent of my random matrix Q by M and G, then I'm quoting for you here two results that are on a fully local scale. The first result says that the Stieltjes transform is approximated by the deterministic equivalent up to an error of 1 over n times the imaginary part of z. And the second is that entry-wise, the resolvent is approximated by the deterministic equivalent up to some spectral scale. This is a result that's due to Li, Schnelli, Stettler, and Yale in 2016. And then the second result is about the approximation of bilinear forms, that if I take test vectors u and v, and I hit it with the resolvent g, it's approximated by the deterministic equivalent g naught. And this is a result due to Knowles and Yin in 2017. These results are fully local now, so they hold down to to spectral argument z with imaginary part down to n to the -1, essentially. For the purposes of this talk today, I'm not going to have any local results. I'm only going to talk about global spectral results. For global results, this parameter is just 1 over root n, and the Stieltjes transform approximation is 1 over n. Okay, so this is the second thing that I want to review. And the third thing that I want to review is a free probability construction of these two deterministic equivalent objects. And the construction goes something like this. You consider an infinite dimensional von Neumann algebra. So you should think about just an algebra of bounded linear operators on some Hilbert space, equipped with a trace. It's an n-dependent von Neumann algebra. So contained inside this is actually your space of n by n matrices. I'll call that M. This is embedded as a von Neumann subalgebra. And you also have a semicircular element, meaning its law under this trace tau is semicircular, and this element is free of this n by n subalgebra, this matrix algebra. So you consider inside this n by n matrix algebra the space of diagonal matrices, and you can define a projection or a conditional expectation from this full von Neumann algebra onto this space of diagonal matrices that sort of satisfies the properties that you would expect of a conditional expectation if you think about this trace as an expectation. So what this means is that if you take the conditional expectation of an element of this diagonal subalgebra D multiplied by an element, you can pull that outside of the conditional expectation. And if you take the expectation of the conditional expectation, it has the usual Tower property. Okay, and the matrix that we're interested in is this deformed Wigner matrix A plus theta. So inside this free probability construction, let me consider the semicircular element little a plus this diagonal matrix theta, which sits inside this n by n matrix space. Then I can take the trace of q minus z inverse, and this gives me exactly the deterministic equivalent approximation for the Stieltjes transform. And I can furthermore take this diagonal projection trace, this conditional expectation, and this will give me exactly as a diagonal matrix the approximation to the resolvent. So this kind of a construction for the Stieltjes transform is explained extremely nicely in this paper by Speicher, Vargas, and Mai in 2011. And this kind of construction for the resolvent, one place you can find this is we used this previously for a different model. This is with Yish Sun and Zhichao Wang, who's here in the audience today. Yeah, this is in some work some time ago. Okay. Sorry, the reason I'm introducing this kind of formalism here is because for the model that we're going to talk about, I only have a description of the limiting measure and the deterministic equivalent at this level and not at the level of the preceding fixed point equation. Okay, so let me explain the results of our work. So the random matrix model that I want to look at is this Kronecker deformed Wigner model. So A and B are independent Wigner matrices, and sorry, let me define actually what that is. So they have independent entries on and above the diagonal. The mean is 0, the variance is 1 over n, and I'm going to assume that root n times the entries have bounded moments of all orders. Theta and xi are deterministic and diagonal matrices. They're bounded in operator norm, and I look at this matrix, which again is A cross I plus I cross B plus theta cross xi. It's n squared by n squared. Okay. The resolvent will be q minus z times identity inverse. The Stieltjes transform is 1 over n squared times the trace because this is an n squared by n squared matrix. Okay. One thing I want to clarify off the bat is that the freeness property in this model, so there is some asymptotic freeness in the model, but there's not asymptotic freeness with respect to the full trace. Instead, the freeness that arises is with respect to these partial traces, where you take the trace in one block, right? One way you can see that the model is not free with the whole trace is that, for example, the first two of these matrices actually commute with each other. A cross I and I cross B are commutative, so they can't be freely independent. Okay. So to define the deterministic equivalence in this model, let me consider again a von Neumann algebra with a trace tau containing as a subalgebra the space of n by n matrices and now two semicircular elements that are free of this n by n matrix space. Let me call them A and B. And again, let me consider this diagonal conditional expectation. So I define this approximating operator, which is A cross 1. 1 is the unit in this algebra, plus 1 cross B, plus theta cross xi. And then the deterministic equivalent approximations are given by the trace of Q minus Z inverse, and then this diagonal projection of Q minus Z inverse. I think one natural question one might ask about this is whether there's a simpler characterization of these limiting objects. We haven't been able to find one, so the simplest characterization I can give is maybe this one, that I can write down a pair of fixed point equations that characterize this thing, but the fixed point equations themselves are also in this operator algebra space. They're not in the scalar field. So I can define this pair of fixed point equations that looks a little bit like the fixed point equation you just saw for the deformed Wigner model. But the solutions are to be understood in this operator algebra space. Then the Stieltjes transform approximation is given by the trace of either of these two things, and I can furthermore construct from this approximation for the resolvent. Okay, but I don't have a characterization in terms of purely scalar fixed point quantities. Our main result for this matrix model is the following. So we have a global result, which is saying the following. For any fixed z in the upper half plane, so it's not a local result, it's a global result, the Stieltjes transform is approximated on the scale of 1 over n. If I look at the entries of the resolvent, this is this picture I was showing you earlier, that the diagonal entries are approximated by the diagonal entries of the deterministic equivalent. The partial off-diagonal entries are on a scale of 1 over root n, and the fully off-diagonal entries are on a scale of 1 over n. We also have an estimate for the m by m blocks. Because this is an n squared by n squared matrix and has this Kronecker-product structure, I think it makes sense to also think about the m by m blocks within this n squared by n squared resolvent. For the m by m blocks, we have these approximations in operator norm, that the off-diagonal blocks are an operator norm on the scale of 1 over root n. The diagonal blocks remain stochastic on an order 1 scale. But if I look at the inverses of the diagonal blocks, their differences are approximated by a deterministic quantity, which is a shift of these diagonal matrices up to an error that's 1 over root n, again, an operator norm. And then finally, if I take a linear form of this resolvent, it's approximated by a linear form of the deterministic equivalent up to an error of 1 over root n. Okay? So these are the results for the random matrix model. And if I apply this now back to this constrain least squares problem that I talked about at the start of the talk, the result would look like the following. So recall the optimization problem we're interested in is something like this. So I write down the explicit solution, and it's going to look like something like a resolvent of the matrix I just wrote down. You need to use a small linearization, but I'm going to hide these details a little bit. And I can write down an expression in this operator algebra construction for the value of the minimizers, right? So I can define this object that involves this A cross 1 and 1 cross B, as well as the diagonalizations of these vectors that are defining the linear constraint. And we can show that the value of the minimizer is approximated by a deterministic quantity that's defined in this way. And if I take a linear test vector applied to the solution, it can also be described in this kind of a way. Okay. One thing that maybe I can try to explain is that, so because we don't have scalar fixed point equations defining these limits, it's not entirely clear how one might compute numerically on a computer, like what is this useful for? So we suggest maybe one way to do this computation, which is, so this quantity that I'm defining here has this inverse of this operator. And what we suggest is that, okay, well, you can do this trick of adding and subtracting this eta inside. You take eta, something to be large, you add and subtract it inside the inverse, and then you do a series expansion in the first eta. So you'll get factors of 1 over eta on the bottom, and then powers of this remaining stuff on top. And if you choose eta large enough, this will be convergent. And because it's geometrically convergent, you can approximate this quantity by computing a sufficiently large number of terms of the series expansion. And the terms of this expansion you can compute rather explicitly. They depend only on the empirical moments of these theta, u, and v vectors defining your problem. And you can compute them through the free moment cumulant relations. I'm not going to go through the details of this, but you can find them in the paper. What this involves is an enumeration over a pair of non-crossing pairings for each of these terms. And we did implement this numerically, and I can show you an implementation of this prediction. So this is an example where n equals 1,000. So we solved random instances of this problem using gradient descent for n equals 1,000. The dots that you see are the mean values of the solution with error bars indicating 1 standard deviation. And then the solid line is what we computed using this kind of trick up to m equals 12 terms of that series. The horizontal axis here is a correlation parameter controlling the correlation between these u and theta variables and v and xi variables defining the problem. And then the 3 different lines are 3 different scalings of the problem. I think the purpose of this picture is just to show you that we can compute this theoretical approximation that agrees quite closely with the numerical prediction. Okay. And let me close this section of the talk with just a description of the related literature. So in the recent 3 or 4 years, in the random matrix theory community, there's been some interest in studying these kinds of Kronecker-product random matrix models. They're not looking specifically at this model that I'm talking about today, but they're looking at something that's more general, which is you take an arbitrary polynomial Q of matrices of this form. You have the Kronecker of some matrices A with an identity, and then the Kronecker of identity with some matrices B. And the dimensions here, so that the A's, let's say, are in m by n, and then the B's might be in some different dimension, km by kn, where k also depends on n. So there's been a series of recent results. Back in 2022, there was a sort of breakthrough paper by Collins, Guionnet, and Perrault, who developed this new method of approximating traces of smooth functions of polynomials of this form. And if you take their result and apply it to the Stieltjes transform, what the result implies is an estimate of the Stieltjes transform by some deterministic object up to an error of scale k squared over n squared. Okay. And this result holds in a setting where your A's are GUE and the B's are deterministic matrices. So as long as k is a little bit smaller than n, you can iterate on this idea and apply this to derive a full asymptotic expansion. And this was done in a couple papers by Perrault in 2023. And actually using this asymptotic expansion, you can actually show a stronger statement of strong convergence of spectral inclusion. That is, it's not just that the eigenvalue distribution of this Q converges to its limit, but in fact, the whole spectrum of Q is contained in the neighborhood of the spectrum of the limit. This was shown by Perrault when the A's are hard unitary and the B's are again deterministic. In this recent concentration, this matrix concentration paper by Bandera, Bodejarjo, and Van Hando in 23, they also explain an analogous statement when the A's are Gaussian matrices, so in the Gaussian context. But it seems that these kinds of results all become vacuous when k becomes proportional to n, which is our setting of interest. Yeah, so somehow k equals n is a sort of like a critical threshold for these kinds of results. And then recently, in 2 works that resolve this what's called this Peterson-Thom conjecture in operator algebra theory, there was a paper by Belinsky and Capitan that showed the spectral inclusion when k equals n, and all of these matrices are GUE. And then there was a paper by Bordanov and Collins that showed the spectral inclusion, in fact, when k can even be exponentially large in n, and the A's are hard unitary. So this last paper by Bordanov and Collins uses a high trace moment method that doesn't give information on the resolvent. This method of Belinsky and Capitan, they do analyze the expected Stieltjes transform. It's a technical tour de force. It's a very heavy paper, and it wasn't clear to us as outsiders, whether the techniques can be extended to understand the resolvent. And whether they can be extended to understand models with deterministic matrix components. And so what we decided to do is to just try to do our own analysis of the resolvent approximation. Okay, so in maybe the last 10 or 15 or so minutes of the talk, let me try to explain some of the high-level ideas of the analyses of how this goes. Yeah. Okay. Okay, good. So I think at a high level of the analysis, the idea is quite simple. We're going to do a two-stage leave one out analysis or a two-stage sure complement analysis. And I think at this high level, perhaps some of the things I'm saying might also apply to nonlinear models. I'm not sure. Okay. So I'm just going to talk about this Kronecker deformed random matrix model. I won't talk exactly about the least squares problem, but that's a corollary of this. So if I look at this matrix model, again, let me remind you, it's A cross I plus I cross B plus theta cross xi. A and B are your independent Wigner matrices, and theta xi are diagonal. So it's a two-stage analysis. In the first stage, let me just condition on B. I fix B as something deterministic, and I just use the randomness of A, and I try to do your usual leave one out sure complement analysis over A. So I can write out the resolvent in terms of block decomposition in terms of this first tensor factor A. And in a block matrix form, the resolvent looks something like this. In each block, you have an entry of A multiplying the identity. And then on the diagonal, you also have this B and then these multiples of xi and then subtracted by z identity, which is in this resolvent, right? So in this expression here, I want to clarify, each element here is an n by n block inside this larger n squared by n squared matrix, right? So we're going to condition on B. And if we condition on B and just look at the randomness of A, the independent structure in this is at the level of these n by n blocks, right? The blocks are independent from each other, but the entries within each block are not. So I think it's very natural to try to do a sure complement analysis or a leave one out idea where you leave out a whole block at a time, right? So I'm going to leave out n rows and n columns at a time. And if I leave out the ith row block and the ith column block and apply your usual sure complement identities, you'll get these kinds of identities for the resolvent, that the ith block of the resolvent is the inverse of this kind of a sure complement quantity, and then the off-diagonal ij block has this expression here. Okay. So I've highlighted in blue the two terms that we need to analyze. So in usual scalar matrix models, the way this analysis goes is you apply some concentration of this bilinear form. You apply some concentration of this linear form. In particular, when you apply concentration to this first block, you'll get back the trace of the resolvent. And then if you average over I, you'll get a fixed point equation in the trace of the resolvent, right? So here, this equation is at the level of m by m matrices. So I think it's quite natural to try to use some matrix version of concentration inequalities to do these things. So we can try to appeal to non-commutative versions of Bernstein or Khinchin inequalities to do this concentration. And if you do this, you'll arrive at the following kinds of things. So for these two quantities that I wrote in blue, if you look at the Schatten P norm, let's say, of these quantities, a matrix Khinchin type inequality will show you that it's controlled by the P norms of these two matrix variance kinds of parameters. And then if you iterate this on itself for the quadratic form, you can get a bound in terms of these two matrix variance looking kinds of parameters, the P norm of G of the resolvent itself, and then this P norm of this partial transpose of the resolvent. So what I mean by partial transpose is the matrix where in this m by n block structure, I swap the blocks, I transpose the blocks, but I don't take a transpose or adjoint within each block. Okay? And statements of these inequalities in the Khinchin case with Rademacher random variables you can find, for example, in a monograph of PZA in '98. And the first complication or challenge that arises that doesn't occur in scalar random matrix models is the following, that not all of these errors that you need to bound in the concentration can be controlled spectrally by the resolvent. In particular, there are these two terms that are related to the partial transpose of the resolvent. There's in general no direct spectral relation between a matrix and its partial transpose. The naive bound for the norm of a partial transpose in our case would be n times the norm of the resolvent itself. And if I apply this naive bound into here, I'll just get a completely trivial bound for this concentration, right? So I don't get anything out of this. So this is the first conceptual issue. I'm going to sidestep this for a second. I'll come back to this very soon, but let me ignore this issue for a second. Suppose that I can actually obtain a 1 over root n kind of bound for these concentration terms, which is what you might expect from classical analysis. Then you'll arrive at a statement that, okay, the partial trace of the resolvent, by this I mean the average of the diagonal blocks of the resolvent, are approximated by a fixed point of this kind of a fixed point equation, right? So this is a fixed point equation in the m by n matrix space. It involves this other matrix B, and the fixed point is this MB. And let me explain how the rest of the analysis goes. So I think the second conceptual issue is now I want to do the second stage of the Schur complement analysis, right? I conditioned on B at first. I did the Schur complement over A. I arrive at this fixed point equation. And I want to now do the Schur complement analysis over B. But here, this fixed point, at least the way I've written it here, MB depends implicitly on B in this rather complicated way, right? So if I want to do some leave one out, it's not clear how I can understand the independent structure here and do this fixed point analysis. So how do I do the second analysis over B? Okay. So let me talk about the second issue first, and I'll come back to the concentration. So the second issue we resolve using this operator algebra construction. So my claim is that the solution to this fixed point equation, it's an m by m matrix fixed point equation, I can write in an explicit form if I introduce this operator algebra. So it's given explicitly by the trace, the partial trace of this quantity here that looks kind of like my original matrix model, except that I've swapped out the first Wigner matrix by this operator, by the semicircular element A. And so this is now an element of A cross C m by n, and after I take a trace, it's just a matrix. It's an m by m matrix, right? And this is now an explicit expression. If I now want to study the Stieltjes transform, in other words, if I want to take another trace of MB, I can first take this trace inside this tau cross I, and I can study the other partial trace and the other factor of this operator kind of expression, right? And now I can apply a second stage of leave one out analysis inside this first trace over B. The only difference is that in the second stage, when I write out the blocks of the resolvent in the second stage, each entry so each coordinate of the block is actually an element now of this operator algebra A. So it's an infinite dimensional object rather than an m by m matrix. But as long as the arguments that we use to do the analysis can hold in an infinite dimensional setting, we can use the exact same methods in the second stage to analyze the first stage. Okay, so now let me come back to this issue of the concentration. So how do we actually get this 1 over root n kind of concentration that we need to arrive at this fixed point equation in the first place? So as an example, let me just consider one of the errors, which is this linear form kind of concentration. And you can do something similar for the quadratic form. So for the linear form, it looks something like this. Let me call this quantity xi. So the approach that we're going to use to do this concentration is the following. We're going to first do the analysis for large z. So if z is large enough, in particular larger than the operator norms of all of the things defining my model, then I can get your usual 1 over root n bound for this error by just doing a series expansion of the resolvent in 1 over z, expanding all of the terms of the series in terms of monomials. You know, you have your elementary tensors and the monomials, and then we can actually apply scalar variable concentration to the first tensor factor. So I'm not going to use these non-commutative concentration. I'm just going to use scalar value concentration. And for large enough z, we can get a bound of 1 over root n for this. Okay. Now, what this implies by a quantitative version of a maximum modulus principle, so this is a resultant complex analysis. If I have an analytic function on the unit disk, and I look at the rings of the disk around 0, and I look at the maximum value of the function on each ring, then the log of the maximum value as a function of the log radius of the ring is increasing and convex. This is a classical result of complex analysis. And if I map that kind of result from the disk to the upper half complex plane using a conformal map, then the statement that we can get is that because I have this kind of 1 over root n bound for large z, and I can use a trivial bound for all z, using this convex interpolation, I can get a weak bound for this error that I want that's of the size n to the minus a. For some small constant a, it's not an optimal constant. That depends on the imaginary part of z. So I can get this weak n to the minus a bound. Now, once we have this weak n to the minus a bound, we're going to use this inside an iterative bootstrapping argument. So we can do a similar, so I talked about this analysis of the linear form. You can do a similar argument for the bilinear form. If you do a similar argument for the bilinear form, then you're going to get an approximation for the diagonal blocks of the resolvent and the off-diagonal blocks of the resolvent at the scale of n to the minus a. Okay. Once we have these approximations, then we're going to show the following bootstrapping lemma, that if these errors are on the scale of n to the minus a, and in infinite dimensional settings, we want to do this in the LP norm rather than the operator norm. Then, in fact, we can bootstrap this to show that these errors, in fact, hold on the scale of the minimum between 1/2 and 3a over 2. Okay, and I'll explain this in a second. But if we have this result, then we can just iterate this result on itself a few times, and eventually we'll hit the optimal error 1/2. Right? So we'll get this error 1/2. And then from here, once we get these errors of 1/2, I think the rest of the analysis for the Stieltjes transform and the linear forms are more standard, so I'm not going to talk about those. Okay. So let me explain how this iterative bootstrapping works. So for the iterative bootstrapping, we are going to use the non-commutative Khinchin inequality that I had earlier. So if I look at the non-commutative Khinchin inequality for the linear form, I have these two terms. The first term here is something I can bound directly spectrally by the resolvent, so I won't talk about it. The problematic term was the second term that sort of involved this partial transpose. So the gist of the analysis is that this quantity that I want to bound, let me call this phi for a second, 1 over n times the sum. I can take each sum end and write its partial expectation over the row and column of A, and then 1 minus its partial expectation. So there's some sort of a centering term and a fluctuation term. And then using the fact that I have this n to the minus A bound for the off-diagonal blocks as input, we can use a version of fluctuation averaging to show that the average of the second term is in fact on a scale of n to the minus 3a. Right? So the naive bound for this would be n to the minus a times n to the minus a, which is n to the minus 2a. And then we can use a fluctuation averaging argument to show that because these terms are weakly dependent, we can estimate it on a scale of n to the minus 3a. Now for the first term here, this mean term, we can use a sure complement identity to do a resolvent expansion of these terms. And after doing a little bit of algebra, what we get back is this MBR. Sorry, I should maybe explain. MBR was the approximation for the diagonal blocks of the resolvent. You get back this thing that's 1 over n times the sum, MBR star. And importantly, we get back the quantity we're interested in, which is phi. This is the error that we started with, okay, plus some error. And so what we arrive at, if you just move this to the other side, is a bound on this phi minus this 1 over n sum over r MBR phi MBR star. So it's a linear operator applied to our error phi is bounded by some better error, which is n to the minus 1 plus n to the minus 3a. This linear operator is something that's appeared in random matrix theory several times before, associated with this Dyson fixed point equation. The important property of this linear operator is that it's positivity preserving, and so it has a Perron-Frobenius eigenvector in the positive cone. In the infinite dimensional set A, it only has an approximate Perron-Frobenius eigenvector. And there's an argument in this paper by Ajanki, Erdős, and Kruger that shows that because of this positivity preserving property, you can argue that this linear operator is actually quantitatively invertible. And therefore, from this quantitative invertibility, we can deduce that the norm of this error phi itself is bounded by the norm of this linear operator, which then is bounded by this. Okay. So finally, if we apply this bound for the norm of phi back to this problematic term of the non-commutative Khinchin inequality, we get the proof of this bootstrapping lemma. Okay, and then applying the bootstrapping lemma on itself, we conclude the analysis. Okay. So these are some of the ideas of the argument. So let me conclude. I think I'm right on time. So in conclusion, I think what I've said in this talk is the following. There seems to be an interesting class of mean field models over matrix value variables that are m by n, and that have this kind of Kronecker-product structure coming from separate constraints or things about the rows and columns of this variable. It's admittedly a very simple linear setting that we studied. Exact asymptotics can be derived using random matrix theory techniques. And the way we do the analysis is this two-stage leave one out analysis, where we use an operator algebra construction as an intermediary to connect the two stages of the analysis. The asymptotic limit in this model, as far as we can tell, seems to have a characterization via fixed point equations only over this operator algebra, but I can't seem to describe it over scalar random variables or fixed point equations in the scalar field. And I think one theme of this workshop, if I'm looking at the abstracts of a lot of the talks, is I think there will be a lot of talks about training dynamics and learning dynamics. I've talked only about the minimizer and the sort of the statics of this problem. Because this is a quadratic problem, of course, you can also write down explicit form of the dynamics. It's spectral. It's a quadratic problem. And then if you want to do some kind of mean theory, so some kind of mean field analysis of the dynamics, I think one can also do this. We didn't do this in this work. But I believe that a description of the dynamics for this kind of model would also have to be in this operator algebra kind of a space rather than over the scalar field. OK, that's all I wanted to say. And here's a reference to the work on arXiv. Thank you.
At the beginning, when you were talking about the original problem that motivated a lot of your analysis, which was the permutation matrix search, right? When you add this regularization, how non-sparse does this X matrix become? Is this something that you've looked at, or?
Yeah, that's a great question. I can tell you what I understand. I'm not the expert on this, but I think that what's known about that problem, if you solve the convex relaxation, okay, we can't solve the permutation problem, but if you solve the convex relaxation, you'll typically get a solution that's actually close to the center of the polytope. It's not actually close to the vertices of the polytope. For some time, I think there was a belief that maybe because it's not close to the vertices of the polytope, it's just a bad relaxation or bad solution. In some of this earlier work we showed, it suggests that actually you can, so even though it's near the center of the polytope, you can still round it in some sense to a vertex and get a meaningful reconstruction. I can say that in practice, when we solve this problem, it seems to give a pretty decent recovery of the permutation if you do this rounding step afterwards. But theoretically, it's not understood, which is what motivated a lot of our interest in this problem. Is this your question?
Yeah.
Okay. Yeah.
So I was going to say that the field of literature on random matrices that you've used also includes results for correlated entries, at least with short-range correlations.
Yes.
But do you have any hope of maybe being able to translate some of them?
To do correlated entries?
Yeah.
Between A and B, or you mean like within each of the Wigner matrices themselves? So I think one thing that would be interesting in this context.
Yeah, you want correlations between A and B.
Yeah, you're right. I think one thing that would be interesting that we knew in this context would be like a correlation between A and B. That I know I haven't thought about this at all, but it's very motivated by this graph matching kind of thing. Correlations within each A and B we also haven't thought about, but it feels like you can perhaps handle that. Because each stage of the analysis is sort of quite analogous to the usual analysis. Yeah, so in some sense, okay, perhaps I shouldn't say too much, but it's plausible that things can go through.
It's a very difficult computation, though.
Yeah. I see. Yeah. So this result of Erdős's group that we're using for the stability of that came out of studying some of these correlated models, and they were studying these matrix Dyson equations, and yeah. Thanks.
Then we'll break for lunch and we'll reconvene upstairs, and we'll reconvene at 1. Yeah. Thank you very much. All the speakers will go on.